In this video, we're going to go over some examples of calculating the standard entropy and free energy for chemical reactions. So the first problem we have here gives us a chemical reaction. It's already been balanced for you, right? So it's got carbon dioxide and water producing C6H12O6, glucose, sugar, and O2, right? So it's saying that this reaction was carried out at 25 degrees C and 1 atm. These are our standard temperature and pressure, right? So just FYI, that's STP, standard temperature and pressure. And it said calculate delta H, delta S, and delta G for the reaction using the data given here, right? So this is a table that gives the standard enthalpy of formation for all of the compounds listed here that are involved in this reaction, and the absolute entropy for all of the substances in this reaction, right? So these values are either going to be given to you or you'll be able to find them in your textbook. Almost every chemistry textbook has a table of thermodynamic properties that is in the back that you can use as a reference to get these values when you need them. Okay, so what do we need to do here? So we need to calculate delta H and delta S. We have the data for that. And we'll cross the bridge of delta G when we get there, the free energy. But the first thing we know we can do is calculate delta H, right? We've been given all of the enthalpies of formation. We can calculate delta H using Hess's law, right? So calculate delta H for the reaction, right? So delta H for the reaction, just as a refresher, right? Basically, you're going to take the sum of the number of moles of the products times the enthalpy of formation for the products minus the sum of the number of moles of the reactants times the enthalpy of formation for the reactants. Right, so we can use this formula directly. We have everything we need. Like I mentioned, our equation is already balanced for us. So we have everything that we need in order to plug in and solve. So let's do that. So we're going to plug and solve. So enthalpy for the reaction. Our products are glucose and O2, right? So the enthalpy of formation of C6H12O6 is going to be negative 1,275 kilojoules per mole, right? It's only 1 mole of this that's produced in the reaction, so we don't have to have a stoichiometric coefficient out front. So we can just put that negative 1,275 kilojoules out front. Okay, now the second product that's formed is O2. And if we look here, O2 has no enthalpy of formation. So like we talked about in the previous course, if it is a diatomic at room temperature, right, stuff like O2, N2, Cl2, what have you, those will all have a 0 enthalpy of formation because they're not being formed at that temperature, right? It just exists naturally in that state. So that's going to be 0. So now we can move on to the reactants. We got 2 reactants, CO2 and water, right? So it's going to be minus. Let's start with H2O, right? So H2O, we got a stoichiometric coefficient of 2 out front, so we'll put that there. The enthalpy of formation for H2O is negative 286 kilojoules per mole. Right, and for CO2, we have a stoichiometric coefficient of 6, right? So we'll have 6 times the enthalpy of formation for CO2, which is negative 393.5 kilojoules. Right, so when you put all this together, we have the enthalpy of the reaction is going to be 1,658 kilojoules, right? So we're releasing a lot of energy here, right? So this is the heat of the reaction calculated from the standard enthalpy of formation data, right? So just using the information given to us in the standard enthalpy table, we're able to plug it in and solve here. Okay, so now we have delta H. So now we can calculate delta S, right? So let's calculate the entropy for the reaction, right? So we got delta S, standard entropy for the reaction, calculated in the exact same way, right? So we use the same Hess's Law type of format. I'll go ahead and write it out here. But delta S for the reaction be equal to the sum of the number of moles of the products times the standard entropy for the products minus a sum of the number of moles of the reactants times the absolute entropy for the reactants. All right, so if we plug everything in here, right, so we can plug in and solve. Again, products are glucose and O2, right? So what we can do here is just plug in all of our absolute entropy values with the appropriate stoichiometric coefficient in order to solve. So first for C6H12O6, we got 212 as the entropy. So we'll have joules per Kelvin, right? And for O2, right now, O2, even though it has no enthalpy of formation, it does, of course, have an absolute entropy because it's not a perfect crystal. So it will not have a zero absolute entropy. Its absolute entropy is 205. So that means we're going to have plus 6 times 205 joules per Kelvin. Right. So that 6, again, comes from the balanced chemical equation. Right. We have a 6 out front of the oxygen. So that is going to come down into this equation. Right. OK, so minus our reactants. Right. For water, we have 2 times 70 joules per Kelvin. And lastly, we have CO2, which has a stoichiometric coefficient of 6 out front, times the absolute entropy, which is 214 joules per Kelvin. Right, so that's going to give us an absolute entropy of 18 joules per Kelvin. Right, so we get an absolute entropy of 18 joules per Kelvin. All right. Okay. So we have the absolute enthalpy. We have the absolute entropy. So now we just need to calculate the absolute free energy. So our standard free energy for the reaction. So in order to do that, right, we already have the absolute enthalpy. We just need to get the absolute free, or the standard free energy. So what we're going to do is use these and plug them into the equation for the free energy, right? Keep in mind that the free energy, delta G, would be equal to delta H minus T delta S, right? Well, we already calculated delta H and we calculated delta S, so we can actually directly plug these in to get our answer. So I'm going to erase a little bit of this to give me some room to write here. So if we plug this in, right, we can say that delta G is going to be equal to, right, our enthalpy, which is 1,658 kilojoules. And let me actually write this off to the side so I have more space. So delta G, 1,658 kilojoules, minus our temperature, right? It's 25 degrees Celsius in Kelvin. That's 298 Kelvin. And our entropy for our reaction, if we convert it to kilojoules, is 0.018 kilojoules per Kelvin. Right? So our free energy for this reaction is going to be 1,652.64 kilojoules. All right. Okay, so that gives us the free energy for the reaction, right? So again, we can actually use our what we talked about previously to note that this process would actually be non-spontaneous, right? Since you have a largely positive free energy value here associated with this process. So this will be non-spontaneous, right? But basically all we did here was use our equation that we talked about in the previous video to get our standard entropy for this reaction. Use the enthalpy equation that we talked about in the previous course to get the enthalpy for the reaction, and then used our free energy association in order to get the free energy for the reaction, right? So basically just kind of tying all of this stuff together, you can calculate a lot of different thermodynamic properties for a chemical reaction. Okay, let's look at another example here. So this example gives us a reaction of SF4 gas with fluorine gas to produce SF6. Right? It says the value of the of delta G for the reaction is 374 kilojoules, while the free energy of formation for SF6 is 1,105 kilojoules. Use this data to calculate the delta G of formation for SF4. So I wanted to highlight this example to show you that just the same way that we calculated the enthalpy for the reaction, the entropy for the reaction, we can do the exact same thing for the free energy for the reaction. So it follows a similar Hess's law as well, right? So delta G for your reaction is going to be equal to the sum of the number of moles for the product times the free energy of formation for the products minus the sum of the number of moles of reactants times the free energy of formation for the reactants, right? Just like with the enthalpy of reactions, the free energy associated with these reactions are also in tables, in textbooks, or online and whatnot that you can find, right? So for this particular reaction, right now, keep in mind, this is already balanced. We got 1 sulfur, 6 fluorines, right? So we don't have any stoichiometric coefficients here, right? So, but for this one, we could say that the free energy for this reaction is going to be equal to the free energy of formation for SF6 minus, right, because it's the only product, so minus the free energy of formation for SF4 minus the free energy of formation for F2. Right. So now, similar to the enthalpy of formation, if something is a diatomic, a homonuclear diatomic at standard conditions, it also has no free energy of formation, just like it would have a 0 enthalpy of formation. So the free energy of formation for F2 is 0. So this actually simplifies this a little bit. So we have delta G for the reaction. It's going to be equal to the delta G of formation for SF6 minus the delta G of formation for SF4. Right, so now we actually have everything we need to solve. So we're trying to use this data to calculate the free energy of formation for SF4. All we have to do is just do a little bit of algebra here to isolate the free energy of SF4, and then just plug and solve from there. So if we do the algebra here, formation for SF4 is going to be equal to the delta G of formation for SF6 minus the delta G for the reaction. Right, so now we just plug in the numbers that we were given. The delta G of formation for SF6 is going to be negative 1,105 kilojoules per mole minus the delta G for the reaction, right, which is a negative 374 kilojoules per mole. Right, so that's going to give us negative 731 kilojoules per mole as the free energy of formation for SF4. right? So like I said, I really wanted to just highlight this example to show you that this same equation can be written for delta G just like it is for enthalpy and entropy, right? So this can be used to calculate the free energy for reactions as well. Okay, so hopefully this gives you a solid understanding of how to actually calculate entropy and free energy for reactions, right? In the previous video, we really just looked at, looking at this kind of in a qualitative fashion, just being able to predict whether the entropy was going to increase or decrease. But here it gives you insight into how to calculate these things for the entropy and free energy for chemical reactions.